Okay, so what I'd like to discuss today is to go on from the focus on purely gas accretion processes, which has been what I've been talking about for the first four lectures here, and now start saying something about how solid material will evolve within the disk. And the way we've tried to divide this up between my lectures and Willie's lectures is that I'm not going to discuss anything to do with collisions or coagulation or, if you like, multiple particle evolution within disks. And so today we're just going to focus on the evolution of single particles within disks, and then later discuss a sort of related topic, which is collective instabilities of many, many single particles. Okay, so that's sort of how we've tried to divide things up, though there will inevitably be a little bit of overlap with some of what we've already heard. Okay, so I'd like to approach this maybe in a slightly non-standard way. So we've been discussing gas physics so far in the context of disks. So I'd like to introduce the study of how solid materials, so dust particles and maybe slightly larger particles of millimeter or centimeter dimensions, I'd like to introduce how those particles would evolve within disks by first of all thinking of the limit of extremely small dust particles, if you like, which would be just other kinds of gas molecules. And the reason for that is that this sort of fits in quite naturally with how we've introduced thinking about the angular momentum evolution of the disk. So let's start here by thinking of a trace species of gas that is embedded within the bulk hydrogen within the disk. So this might be carbon monoxide, it might be water vapor, it might be something like that. Okay. So let's define the concentration C as being the surface density of that species normalized to the overall surface density of the disk. So the assumption that this is a trace species of gas implies that this C quantity is going to be small. So it might be 100th or 1,000th or some number like that. Now, the trace species, let's just again take the very simplest case. Let's assume that that is neither being created or destroyed. So we can have different models where it is created or destroyed, but in the simplest case, let's assume it's conserved. So we would have a continuity equation for this trace species sigma d. Okay. Now, if this species is embedded within the gas disk, diffusion will tend to equalize the concentration between different places within the disk. So if that diffusion depends only on the gas properties and not on the properties of this trace species itself, then the flux of this trace species will have two pieces. First of all, if the gas is moving with some velocity v, then the trace species of gas will be moved along with that velocity. Okay? So there'll be advection with the mean gas flow f v there. And then there will be diffusion where there is a gradient in the concentration. So if we have regions where there is a high density of this trace species, and they're adjacent to regions where there is a low density, diffusion will tend to produce a flux between those two regions there. Okay. Okay. So we can take this equation for the flux, and we can combine it with the surface density evolution equation we previously derived for the gas. And when we do that, we end up for an axisymmetric disk with a new equation that's rather similar to the evolution equation for the surface density, but which now describes the time evolution of this concentration. Okay? And so for the concentration, we have a piece that's really quite similar to what we just had for the surface density, a diffusion equation that involves the second derivative with radius of the concentration, and it depends on how diffusive the disk is. Okay? So in the previous equation we had for the surface density evolution, we had the viscosity of the disk, which was reflecting how efficient turbulence was within the disk at redistributing angular momentum within the flow. Here we have quite a similar equation, but it involves how diffusive the disk is. If we have turbulence, for example, how effective is that turbulence at equalizing the concentration, say, of this water vapor within the disk. So this is very similar to what we had before. And then we have a second term, which involves the radial velocity in the disk and just one derivative of the concentration, which is just reflecting how the concentration of this trace species is advected due to the motion of gas within the disk. Okay. Now, if we assume that the disk is also steady, then we have an expression that I think we saw just before the break. The radial velocity is just minus 3 nu over 2r, where nu is the viscosity. Okay? So in a steady disk, this radial velocity term just depends on the viscosity and the radius. And that just reflects that at different points in the disk, the gas is moving in at different speeds, and so we're trying to sweep, say, this water vapor in at different rates. Okay? Now, we can look at solutions of this kind of equation, which was, I think, first derived by Morfill and Volk in maybe the early 1980s. And what's found is that how those solutions look depends very strongly on basically how strong this radial velocity is, which is trying to sweep everything inwards, compared to how strong this diffusivity is, which would be trying to spread everything out and equalize the concentration at different radii. So what you can do, you can take a simple model where let's assume that we have our disk, and then at some particular radius, maybe at 1 AU, we just release a bunch of this trace component of gas, and then watch as it is both moved inwards by the inward flow of the gas disk, but then is also trying to diffuse outwards to equalize what's initially a very non-equal concentration. Okay? So you can then ask, suppose we're at some other radius in the disk, perhaps at 10 AU, how much of that material we released at 1 AU ever makes it beyond 10 AU before eventually, of course, it will all get swept in as the disk evolves. Okay? So that's what's plotted in this plot. This is the probability that gas initially released at some fiducial radius of unity here, that gas is first of all diffused out to some radius x, and then gets past that distance x before it eventually comes back in. Okay? So all these curves come up towards unity as we go towards 1. And what we see is that obviously as you go further away from where the gas was released, these curves all go down, because generally speaking, you have to go much further out, you have to diffuse much further out, and that has to be beat out the radial advection. But then they also depend on this ratio of the viscosity to the diffusivity, which is often described in this context as the Schmidt number, though there are various different definitions of the Schmidt number. So if this Schmidt number is 1, that implies that the turbulence in the disk is equally effective at mixing angular momentum, and therefore giving us angular momentum transport and viscosity, and mixing a trace species and giving us a diffusivity. And we get some particular fairly steeply falling off curve in this plot. You can see this is a logarithmic scale here. If, on the other hand, we make the Schmidt number large, so make it 10, say, so that implies that the viscosity is much more efficient than the diffusivity, then that says that the advection term wins. Material is just swept inwards, and it never has a chance to diffuse to large radii. So that curve drops much faster. If we, on the other hand, make it 0.1, we make the disk very diffusive, then releasing material at small radii, it has a chance to spread to large distances fairly easily, and the advection term is much less important. Okay, so we get this rather strong dependence on what this Schmidt number actually is. Okay, so that raises the question, well, if we have a turbulent disk, and maybe the turbulence is described by one of the processes we've discussed earlier in the week, like the magnetorotational instability, what sort of ratio of diffusivity to viscosity is produced in that kind of turbulence? And in general, this quantity may be different for different kinds of turbulence. So if the disk has a lot of vortices in it, for example, the vortices may be very different in how effective they are at diffusing particles and gas compared to how much angular momentum transport they produce. So here are some results for MHD turbulence in disks. This is work by Zhao Zhu and collaborators. And here's a bunch of different simulations that are both in ideal MHD, which we said only applied close to the star, and in ambipolar MHD, which would apply far from the star, where the density is rather small. And what's plotted is the Schmidt number, in the vertical direction for vertical diffusion, and in the radial direction, which is what we're really talking about here. And these are different simulations with different parameters used, basically numerical parameters determining what those simulations are like. And what you can see is that generally speaking, this radial Schmidt number here, the blue points, are within maybe a factor of 2 of unity. In other words, in the radial direction at least, the sorts of realistic turbulence we think are present in protoplanetary disks are roughly equally efficient at mixing material, producing diffusion of species, and mixing angular momentum, giving viscosity and allowing gas to accrete. There are larger variations in the vertical direction, which would be important for the settling of dust particles and quantities like that, or for example asking whether how well water is distributed vertically in the disk when it can condense into ice in some locations and things like that. Okay, so that's how gas would behave. So we've started with gas. Let's now ask, how would things be different if we start considering particles? So now we're thinking about dust particles, which are not identical, if you like, to the hydrogen gas, but potentially have some quite different dynamics. Okay. So if we consider very small particles, so micron-sized or perhaps submicron-sized particles, then even though in principle those may be different from the gas, in practice, the aerodynamic drag between those very small particles, which have a large surface area to volume ratio, that will be so strong that they're really coupled very, very directly into the turbulence. Okay? So very, very small dust particles, we might as well really consider them as if they were gas molecules, and they will basically just obey exactly the same equation that we had before. However, if we have large particles, things are rather different. So first of all, this radial velocity, which in the previous equation was just the radial velocity of the gas, will now have to include the fact that those larger particles are suffering radial drift for the reasons we've already discussed, and which I'll recap in a couple of slides, and will be moving generally towards the star more rapidly than the gas. And as we'll see, for certain size particles, that radial drift can be much faster than the gas velocity, and so this radial velocity, this advection term, will really be much higher than it was for the gas. So generally speaking, that will mean that the particles will just move inwards, and the role of diffusion will tend to be smaller just because the radial velocity is higher. But then there's a second term, which is that this diffusion coefficient here, then in principle may be different from the gas viscosity for 2 reasons. First of all, as we already mentioned, the diffusion and the viscosity that leads to angular momentum transport are in principle sort of different aspects of the turbulence. So those quantities, even for gas, may be different. So that's the Schmidt number thing I was just showing on the previous slide. However, if we then go to a really large object, maybe a boulder, then clearly that boulder has a lot of inertia, and even if the gas is turbulent, it won't actually cause that boulder to drift radially in a diffusive way very strongly. Okay? So when we go to a large particle, there are 2 effects. First of all, there's this effect that the radial velocity is different, and then this effective diffusion coefficient, which enters into this first term of this equation, will be size dependent as well. Okay? So we need to include both of those effects if we want to understand how particles of all different sizes will tend to be moving radially and diffusing within a turbulent disk. Okay, so let's first of all think about this aerodynamic drift term that leads to radial drift. So we've heard quite a lot about this already this week, but I don't think we've actually written down the actual equations that we use to derive that. So let me first just mention that. And to recap, this aerodynamic drift that we're interested in occurs because there's a pressure gradient in the gas, and that pressure gradient generally is such that the gas is partially supported against gravity by that pressure gradient. The pressure is high, close to the star, it's low further out, so there's a radial pressure gradient that partially supports the gas against gravity. So because it's partially supported by the pressure gradient, the gas doesn't need to have such a high azimuthal velocity as it would if there were no pressure gradient. So the gas is generally slightly sub-Keplerian. The particles, if you like, would like to be Keplerian, and so they suffer this headwind, this aerodynamic headwind, which causes them to spiral in. Now, a little bit more formally, you can write the particle equations of motion. So here, the Vr and V phi here would be the velocities, the radial velocity and the azimuthal velocity of the particles within the flow. And the point here is that these have terms here on the right-hand side, source terms, that depend on the difference in velocity between the particles and the local velocity of the gas. And the strength of those terms is defined by the stopping time, which we heard about earlier, the time scale on which aerodynamic drag would slow a particle that is initially moving with some velocity relative to the local gas velocity. Okay. So you can take these equations and you can make some moderate approximations. So for example, you can assume that over a long time scale, the particles will not actually really be accelerating strongly, so they'll just be moving at their terminal velocity. And you can generally assume that because everything is quite close to Keplerian, that the deviations from Keplerian orbits are rather small. Okay? So you can make some fairly well-founded approximations, and quite straightforwardly reduce these equations into a form that gives you directly what the difference is between the radial velocity of the particle and the radial velocity of the gas, and ultimately what the radial velocity of the particle itself is. So when you do that, you get a very simple looking expression for what the radial velocity of a particle embedded within a gas disk, which in principle has a non-Keplerian velocity profile, looks like. So what we've done here is to define the azimuthal velocity of the gas in the same way as we did before. So that's the Keplerian velocity with this correction factor eta, which just depends on the pressure gradient in the disk. So that will depend on how hot the disk is and what the gradient of its surface density and temperature profiles are. And then we've defined the stopping time in a dimensionless form tau, which is the non-dimensional, the real stopping time t-stop normalized to the Keplerian angular velocity. Okay? So we have this parameter tau here reflecting how well the particles are coupled aerodynamically to the gas, and this parameter eta reflecting how far the gas deviates from Keplerian velocity. When you do that, the radial velocity of particles depends on the radial velocity of the gas, multiplied by this tau to the -1. It depends on how non-Keplerian the gas disk is, and then via these terms on the bottom and this term on the top, it depends on the size of the particle measured in terms of the dimensionless stopping time. Now you can plot that for a fairly reasonable disk model. So let's say we're at 5 AU, h over r is 0.05, and alpha, which enters here just in determining what the radial velocity is 0.01. And here's what you get. This is the radial velocity normalized to the Keplerian velocity as a function of the dimensionless stopping time. Okay? So if you have very small particles, those are well coupled aerodynamically to the gas. They just move in at whatever the gas speed is, which in this particular model is a few times 10 to the -5 of the orbital speed. Okay? Very, very large objects are aerodynamically decoupled from the gas, and they basically don't move in at all. They have a very, very slow radial velocity. But in between, you have some regime where the aerodynamic drag is strong, and it peaks at this dimensionless stopping time of unity. And the point to notice, which was already discussed earlier in the week, is that the value of that radial velocity is very high. Okay? So here, it's exceeding 10 to the -3 of the Keplerian velocity. Now that may not seem like very much. 10 to the -3 is a small number, but remember the Keplerian velocity is defining really the orbital velocity of the object around the star. So if we're out at 5 AU, the orbital time is 10 years. A radial velocity that's a few parts of 10 to the -3 there implies an inward drift speed that's less than 10,000 years. So that's a very, very short timescale compared to the disk evolution timescales we were seeing, for example, in this morning's lecture. So this is the radial drift problem. If we have particles with dimensionless stopping times around unity, their radial drift relative to the gas is very, very fast, and they will drift in towards the star and potentially be destroyed on a worryingly short timescale. Okay, so that's the radial velocity term in that equation describing the advection and diffusion of particles within a turbulent disk. Let me now just say something about how the diffusion term would be expected to vary with particle size. We've already said that if we're thinking about very small particles, those will be very well coupled to the gas, and so those small particles will diffuse in the same way as gas molecules would in the disk. But what about larger particles that, if you like, have a large amount of inertia? Well, there's various arguments you can use to work out what the diffusion is in that case, which in some sense become quite complicated. But I want to just give a flavor of how these calculations are done. So the details in this specific case don't matter too much, and they've been quite simplified for the purpose of this presentation. But I want to just give a flavor for basically how you do this kind of calculation. So what you generally do is you describe the turbulence that is producing the diffusion of the particles as being eddies. Okay? And we'll justify why that's a reasonable thing to do in a minute. And let's assume that these eddies, so here are these eddies in the disk, they have some characteristic time scale, and they have some characteristic of velocity. Okay? So we can make that eddy turnover time scale, T eddy, dimensionless in the same way as we did for the stopping time by multiplying it by omega, which is the Keplerian angular velocity at the radius which we're considering. And we can do this then in various different regimes where this tau eddy can be smaller, larger than the stopping time, and so forth. So let's just consider one limit, the simplest limit, where the particle has a stopping time tau, where that tau is much larger than 1. So now we're talking really about quite a large particle, so getting towards perhaps meter sizes or larger than meter sizes. And we'll consider the eddies to have a small tau eddy, much smaller than 1. In other words, reflecting a turnover time that is much shorter than the orbital time at the radius where these eddies are being considered. So the picture then is to consider a time scale omega to the minus 1. So that's 1 over 2 pi of the orbital time at that radius. And during that time, the particle will receive a number of, if you like, independent kicks from these eddies, which will be tau to the minus 1 eddy kicks. Okay? So during that 1 over 2 pi of an orbit, the particle will, if you like, feel n different eddies, and each of those will give it a velocity kick, which will tend to ultimately accumulate some velocity compared to what the particle had originally. So we'll have that many kicks, and each of those will give the particle a velocity perturbation that is just the ratio of this eddy turnover time to the particle stopping time. And that will then be multiplied by the characteristic gas velocity. Okay? So that's just reflecting the fact that if we could kick the particle for its stopping time, we would actually, if you like, significantly change its velocity. If we kick it for a fraction of its stopping time, we just get a proportionally fractional perturbation to the velocity as a result of that kick. So we take these kicks and we add them up as a random walk. So if we have a random walk, we have lots of independent kicks, n independent kicks. When we add them up, we get generally the square root of n times the magnitude of the individual kicks. So we add up those kicks as a random walk, so we pick up this factor of root n, and that gives us an expression for what the velocity perturbation would be after time omega to the minus 1 when this particle has experienced this number of kicks from being bounced around inside the turbulent disk. Okay. Now we can then ask how far will the particle have traveled? Well, it's collected this much velocity over this much time, so we just multiply those together to get the distance traveled, and then that distance implies an effective diffusion coefficient for the particle, dp, which is just the diffusion coefficient in the gas divided by tau squared. Okay? So if you go through those equations, probably best to look at the versions that we posted on the website, you'll find you get this relationship, 1 over tau squared for the diffusion coefficient. Now we've already said that for small particles, the particle diffusion coefficient would just be the same as the gas diffusion coefficient. So if we sort of interpolate between those two regimes, you would generally expect that the ratio of the particle diffusion to the gas diffusion will be something like 1 over 1 plus tau squared. So small particles, very small particles, will be bounced around in the turbulence just as if they were gas molecules. Once they get larger than tau of 1, they sort of rather rapidly decouple from the turbulence. They're still being buffeted by the turbulence, but their inertia basically prevents them from actually diffusing very, very fast. So that's a sort of hand-waving analysis of this kind of thing. This agrees with a much more formal analysis by Udin and Lithwick in 2007, from where actually I've borrowed this simple analysis in turn. And the Udin and Lithwick analysis, which is an analytic calculation, in turn agrees with measurements of particle diffusivity, at least in ideal MHD turbulence, that again have been done by Zhao and Zhu, whose results I was showing previously. So here's a plot from Zhu's paper. This is the stopping time. This is the particle diffusion. For small stopping times, the particle diffusion is just flat, as you would expect from this expression, and then it has this sharp fall off as you go to large particles. So this is the sort of transition we expect to happen in disks. If we have small dust particles, then they are both affected by the inflow of the gas, by any radial drift they have, and also by turbulent diffusion. So all of those processes are acting together for small particles. As we go to larger particles, well, first of all, as we go to tau of 1, the radial drift peaks. So those particles are really trying to move in very rapidly because of the radial drift. But at tau of 1, they still, in principle, have a diffusive component to their evolution due to the fact that they're being buffeted by turbulence. As we go to particles that are larger than tau of 1, which would be particles larger than meter sizes at 1 AU, those particles start to have slower radial drift because they then have more mass compared to their surface area, and they also have much smaller affected by the turbulence because they have so much inertia that they're not really being buffeted around very much by the turbulence in the disk. So we go from small sizes, very small sizes are very diffusive, and the gas radial velocity matters the most. Intermediate sizes move in very fast by aerodynamic drift, but there's still a diffusive component. Very large sizes basically just stay put, and the diffusion component becomes very small. Okay, so that's how we calculate the evolution of a small particle population in the disk. Something I want to mention, though I'm not going to go through any details of this at all, is that basically the same kind of argument, almost exactly the same kind of argument, is used to derive the mutual collision velocities you expect between particles of different sizes in the disk. And the standard reference for this is work by Chris Ormel and Jeff Cuzzi from 2007, and more recent work by Pan and collaborators in 2014. So here's a plot from one of those papers, relative velocities of particles in turbulence, where now we consider two particles in the turbulence and ask if they come close to each other and collide, what sort of collision velocity would we expect? And the same kind of considerations apply here. If the particles are very small, then they're very well coupled to the turbulence. So individually, the particles will be moving around at the speed of the turbulent eddies, but two particles that are very close together in the turbulence are experiencing almost the same turbulent velocity field. So their mutual velocity will actually be very small because they're really just being swept around by the gas, and the gas is not a collisionless system. The gas is a fluid system. Okay? Now, larger particles will be partially decoupled from the turbulence, and so as the turbulence is swirling them around, they can actually have a larger mutual collision velocity when they encounter each other. So that's what's shown here. This is log of the stopping time of one of the particles versus log of the stopping time of the other one. So this is effectively particle size measured in terms of stopping times. And then these are contour plots showing what collision velocity you expect for all different pairs of different particle collisions. Okay? So there's two things to say about this. One is that all of these calculations are very different from the sorts of things we were talking about earlier in the week, where we were talking about magnetic turbulence and non-magnetic turbulence and so on. When we think about these processes, we instead think of fluid turbulence that is really described by eddies and would be described by the sort of normal Kolmogorov theory. And that's generally, we thought, to be a good approximation because these processes are taking place on very, very small scales compared to the overall scales of the disk. So on those small scales, we don't really expect whether magnetic fields are present or how the turbulence is being driven to make a large difference to the properties of that small-scale turbulence. That's reflecting the fact that the Reynolds number, the true Reynolds number of the system, is very large, so there's a large-scale separation between the scales on which, say, magnetic fields might be driving the turbulence and the scales on which dissipation will be taking place, which is where these collisions will also be taking place. So the general results that are found from these kind of calculations is that turbulent diffusion, as we've already said, is rapidly negligible for tau greater than 1. And if we consider smaller particles, then either this turbulent component to the collision speeds or differential radial drift can be the dominant factor determining the collision velocity. Okay? So if we have two particles of different sizes, they will be trying to drift in radially at different speeds, so that will immediately give them a natural collision velocity. But if the gas they're moving in through is also turbulent, then the turbulent velocity will also give them a component to their collision speeds. And depending on how turbulent the disk is, and where we are in the disk and what the particle size is and so on, either of those two terms can dominate. So some of the uncertainties you see in collisional models for particle growth come about from the fact that there is this basic uncertainty. We don't actually know the distribution of collision velocities all that well, and in particular, if the turbulent piece matters, then some of the collisions occur at very low speeds just by chance. Other collisions occur at very high speeds because one particle has really been accelerated to high speed in the turbulence. So there's a much broader distribution of collision velocities in that case. Let me mention one application of these kind of issues, which is related to this, some of these questions of thermal processing of solids that we heard a little bit about from Leonardo. There was a number of years ago a Stardust mission which collected particle samples from a comet. Okay? And so this is a picture of one of those samples from Brownlee et al. In 2006. And what was found in the Stardust mission, somewhat surprisingly, was that from that comet there were both crystalline silicate particles and also some of these calcium aluminum inclusions that we've already heard about. And both of those are in principle quite surprising. So to make crystalline silicates, it's generally thought you need temperatures that maybe are of the order of 1,000 degrees Kelvin. And to make the CAI particles, you probably need even higher temperatures, right? And in fact, as we saw earlier, the evidence is that the CAI particles were only produced very early in the protoplanetary disk lifetime, when presumably the temperatures were at their highest. Now, you might think that those high temperatures would only be present very close to the star, well inside 1 AU away from the star. However, these samples were recovered from a Jupiter family comet, which probably formed instead out at tens of AU away from the sun. So how did those particles get, some of these are maybe tens of microns in size, how did those particles get from very close to the sun out to the comet-forming region to be incorporated into the comet and then sit around for the rest of the lifetime of the solar system? So you can apply the kinds of considerations we've just been giving to ask whether upstream radial diffusion through the turbulent disk could take those particles that you form close to the star and move them out to the comet-forming region. And when you try that, the answer you find is that it's actually very difficult to get those particles from close to the star and put a large number of them out in the comet-forming region. So here's actually a little bit of a mystery. We see these high-temperature condensates in materials that are retrieved from far out in the solar system, and actually how they got there is really quite unclear. Okay, so let's take a 5-minute break at this point, and then we'll continue to discuss some of these collective instabilities after that.
questions quickly at the end of this, just how many would be interested in having you guys walk around during the 5-minute pause during your own lectures? It might give the people at the back of the room a chance to grab you, if that's okay with you. Is that all right?
Yeah. Okay, so that was the first part, and so that first part was quite technical. So that was the simple physics that I've tried to go over in a little bit of detail. The remainder of the lecture today is going to be more complicated physics that I'm not even going to try to go over in detail. Okay, but I'm going to show some cool movies, so maybe that's better, right? Okay, so what we've discussed so far is a picture where the gas disk has some particular properties, and the one that matters has been how subkeplerian it is. Okay, and then the particles respond to that gas disk. Okay, so the gas disk has some non-Keplerianness that leads to radial drift. It also has some turbulence, which leads to diffusion, and individual particles, respond to that in various ways that depends on their size. Okay. Now, if we want to make planetesimals, so we want to make first large macroscopic objects that are many kilometers in size, in many models, not in every model, but in many models, a prerequisite for doing that is that locally we accumulate solids such that the local density of the solids is somewhat comparable to the local density of the gas. Okay? That's, as I say, not an absolute rule, but it's sort of a rule of thumb. Many planetesimal formation models need that. So they need a lot of either settling of the particles or concentration of them from some other mechanism in order to produce planetesimal formation. Now, if you get to a point where the local density of the solids is equal to the local density of the gas, then the idea that the gas disk is, if you like, a passive background that doesn't really care about what the solids are doing clearly breaks down. At that point, there's as much mass in solids in each volume as there is gas. And so really, the solids and the gas have to be treated on an equal footing. And in particular, if you have solid particles which are losing angular momentum to the gas and therefore spiraling inwards, that angular momentum they've lost is then not a small perturbation to the gas, it's potentially a large perturbation. So the gas gains angular momentum from the particles, and indeed it would want to move away from the star if it remains on circular orbits. Okay? So if we have this kind of situation, things are changed. And the first question you might ask is, well, how is the radial drift equation, which I plotted up earlier, how is that changed in that limit? And then is that radial drift solution stable? Okay, so this slide is mainly meant to convince you that this is a complicated problem. Okay, but the good news is someone's worked it out for us, right? So we don't have to worry. So these are the equations for how this works in a relatively simple limit. Okay, where we consider that the gas disk is incompressible. So if there's turbulence in the gas disk, we assume that turbulence is very subsonic, and so to a first approximation, the gas remains incompressible, and we have gas. And we have solid particles which are interacting with each other purely through aerodynamic forces. Okay? So we have 4 equations here reflecting continuity for the particle fluid, for the gas fluid, and then momentum evolution for both fluids as well. Okay? So here's the incompressibility condition for the gas. The divergence of the gas velocity field is 0. Here's the continuity equation for the particles, which have local volume density rho p and velocity Vp. Okay? So these are continuity equations. Here is momentum for these particles. And the point here is that the particle momentum equation and the gas momentum equation have, if you like, symmetric terms on this right-hand side, reflecting the exchange of momentum due to aerodynamic forces. So these are the same kind of equations that I was showing for a single particle. So you see they involve the difference between the particle velocity and the gas velocity divided by the particle stopping time. But now we don't just consider the particle momentum equation, we also consider the gas momentum equation, which has basically the same term with the opposite sign. Okay? And the strength of this gas feedback, of course, depends on the local density of the particles and the local density of the gas. These terms are directly equivalent if we're in this regime where the particle density and the gas density are actually the same, okay? Which is what we just said. So you can take these equations and look for the equilibrium solution for the radial drift in that case, and that's a solution by Nakagara and collaborators in 1986. Okay? And the solution is fairly complicated, but let me just show one example of that to sort of demonstrate what it depends on. So what's shown here is the sum of the particle radial velocity and the gas radial velocity. Okay? And just as in the simpler form I showed before, it depends on the particle stopping time, it depends on how non-Keplerian the gas disk is, defined by this parameter eta. But what it also depends on now is explicitly on the gas density, the particle density, and how those densities relate to the total density rho, which is just the sum of the two particles. And what you can see here is that there's this term rho gas minus rho particle. If the gas and the particles have equal densities, then this sum of the velocities is 0, reflecting the fact that in that limit, the particles are giving up momentum to the gas, and the rate at which the particles are moving in is exactly compensated by the rate at which the gas is moving outwards. So this is just basically a generalization of the previous formula to allow for the possibility that the particles really have a non-zero feedback on the gas, as well as the gas having a dynamical effect on the particles. So you can look at this paper, or this paper by Udin and Goodman, which is where these equations came from, who state the full solution here for how the particles behave and how the gas behaves, depending on the gas properties, the ratio of the gas and the solids, and so forth. Okay? So that's the equilibrium solution you should use if you need to worry about circumstances where the local particle density is comparable to the gas density. However, the question I want to instead turn to is whether that solution is a stable solution. Okay? And a more recent result, which dates to this paper by Udin and Goodman from 2005, is that that solution is actually not a stable solution in many circumstances. Okay? There can be circumstances in which this Nakagara et al. Solution is linearly unstable to the growth of clumps in the particle distribution. Okay? And the ingredients of this instability are ones that we'll sort of be talking about partly for the rest of the week. One way of thinking about this is that if you took the gas and you made a slight pressure maximum in that gas, dust would tend to pile up within that pressure maximum. And then the way it works is that the feedback the particles have on the gas tends to actually strengthen that pressure maximum in the gas, which then attracts even more particles, and then sort of has a vicious cycle where the gas continually gets a stronger and stronger pressure maximum as more and more particles clump up in that region of the disk. Now, in an earlier version of these slides, I had a tremendously complicated equation in extremely small font, which fit in between here, which I've deleted, but which you can go and look in Udin and Goodman if you want. So instead, I've put a more bland statement here, saying that even the simplest description of this process mathematically is quite complicated. Okay, so the simplest description is to assume that particles always move at their terminal velocity, which is the same approximation we made in deriving the usual radial drift form. But even in that case, you end up with a quite complicated third-order dispersion relation that depends on the stopping time, on the mass fractions in solids, and the mass fractions in gas, and so forth. So it's really a rather complicated thing that doesn't have a very easy, intuitive explanation. Okay, but here are some results from this Udin and Goodman paper. So what's being plotted here is the growth rate of this instability, which is described as the streaming instability, as a function of the particle stopping time, so this dimensionless tau here, and the ratio of the particle density to the gas density. And these contours here are contours of the growth rate normalized to the angular velocity. Okay? So what's found here is that these linear growth rates are primarily a function of this stopping time. So if the particles are very well coupled to the gas, in other words, they have very small stopping times, then the growth rates of these instabilities are very small. So this is 10 to the minus 4. This is on a log scale. So that's 10 to the minus 4, so it's occurring 10,000 times more slowly than the dynamical time scale in the disk. However, if you go to larger particles, these growth rates climb rapidly and eventually reach a reasonable fraction of the dynamical time in the disk. Now, generally, this clumping, when it occurs on small scales, much smaller than the disk scales, and the basic competition you have is how quickly this clumping of the particles occurs compared to how quickly the particles all move in towards the star. So if you imagine that the particles initially started off rather uniformly distributed, and this mechanism is trying to clump them up into rings and clumps, that is competing against the fact that they're all moving towards the star and potentially will be lost if they get to small scales. So it mostly depends on this stopping time, but then there's also this dependence on the local particle density to the gas density, which is, as you can see, rather complicated. Actually, the growth rates vanish identically if those densities are equal. Okay, so here's instead a movie of what this looks like. So this is the radial direction here. This would be the vertical direction. And what you're going to see here is the density of the particles relative to the density of the gas. Let's go back. You start with a uniform density, and then as the instability progresses, that uniform density breaks up into lots of clumps. Okay. Show that again. You start with a uniform density. As the instability progresses, you get this turbulence, but now turbulence in a gas and dust fluid, and the dust comes into clumps, which have rather large concentrations compared to the background concentration in the gas. And I should mention there's a poster on this very topic just outside, which has many more pictures of what this kind of instability looks like. Okay, so what's physically going on there? Well, there's no actual very perfect analogy for what this streaming instability is like. Here's a sort of a flow chart of it from a quite useful paper by Jacquet and collaborators from a few years ago. A simpler analogy that's often used is a peloton in the Tour de France. Okay, so if you have the Tour de France, you have a whole bunch of cyclists. If they all cycle 20 meters apart from each other, so they're all moving independently through the wind, that requires a lot of energy. If they group together into a peloton so that the leader shields the people behind from the wind, then they manage to move forward with less energy, right? Only the first person needs to be taking the strongest drugs, right? The rest can have less, can be riding a bit cleaner. Okay, so that's sort of what's going on here, right? So here we have dust particles rather than cyclists. If the dust particles are feeling this aerodynamic drag, that will be causing them to drift in radially. If they all clump together, locally they have a density that is comparable to that of the gas, so they can feed back onto the gas velocity field, overall experience less drag, and move in radially less quickly. Other particles that are further out in the disk will still be spiraling in more quickly. They will join the clump and make the clump stronger, which in turn will mean it moves in even slower, and so on and so forth. So you'll get a clumping effect from that. Now, this is an imperfect analogy because actually a peloton is formally a nonlinear system, right? Things have to really clump together very strongly for that to work, and the streaming instability is actually a linear instability, so it doesn't quite describe the early growth of this kind of instability. But it's a good way, perhaps, of thinking how it happens. Now, what kind of densities do we get from that kind of process? Well, here are some simulations by Juning Bai and Jim Stone. These are two-dimensional numerical simulations, varying the overall gas-to-dust ratio, here considering equal mass in logarithmic bins of stopping time. And these are models where the smallest particle size is varied. So what's shown here is time and concentration of particles relative to the initial density. And the point simply to note is that for some ranges of parameters, so here's a system with the stopping times between 10 to the minus 3 and 1, then the peak concentration of particles you can get out of this streaming instability can be very large. So this is a factor of 1,000 here in the concentration compared to what it was originally. So this kind of instability, if it operates, can really clump together particles very, very strongly, such that locally their densities are vastly higher than they would be overall within the disk. Here's another recent calculation by Carrera and collaborators asking when this streaming instability would work. So here we're plotting when the instability would work in the frame of the stopping time here and the solid concentration in the disk just when the solids are smoothed out over the gas disk. So the standard gas-to-dust ratio, or dust-to-gas ratio of 10 to the minus 2 would be down at the bottom. Here we would have higher local concentrations of solids. And this green region here is the region where the streaming instability would be expected to happen and to grow rapidly. Off to the right, radial drift would tend to be faster, and off to the left, the particles wouldn't settle into a narrow enough layer in the midplane to trigger these kind of instabilities. So what you can see here is that there's a fairly broad range of parameter space where this could happen, providing that the particles that are involved have already grown to stopping times of maybe 1/10 and are somewhat concentrated in terms of their overall dust-to-gas ratio compared to the factor of 1/100th, which would be the sort of normal factor we'd expect in protoplanetary disks. What can happen then if this instability proceeds? Well, the general idea is that maybe this could produce a way of producing planetesimals through gravitational collapse. So let's show another movie here. This is now R, and this is the azimuthal direction. Again, we're looking at the over-concentration of solids. So now you can see the shear in the disk, and you can see these clumps forming as a consequence of this streaming instability. So we're going to let this movie run for a little bit, and then when the clumps become very dense, we're going to turn on self-gravity, and you'll see that these dense clumps just collapse into small bound objects within the disk. So this is a way where potentially you can form some of these first planetesimals rather rapidly through a sort of two-stage process. You start with this fluid-gas interaction, which produces very dense clumps of particles, and then gravity acts on those very dense clumps of particles and causes them to collapse into quite large bodies, typically, directly through gravitational instability. So you can see this takes quite a long time. It's still a fairly slowly growing instability, but we're now getting a sort of clumpy ring of solids, which is forming here, within which the density is really rather quite high. And in a little bit, let's try to speed up this movie somehow, we're going to turn on self-gravity, and you'll see these clumps break up into individual objects. Okay, maybe about now. So you can actually see here that within this clump or ring of particles, the radial drift has almost stopped. Right? The particles are dominating the gas to such an extent. There we go. So now we've turned on gravity, and now it becomes very boring because we just end up with a whole bunch of individual clumps. So gravity has really collapsed everything together, and a reasonable fraction of the solids has gone down into individual objects. Okay, so here's then some earlier work by Anders Johansson and collaborators, just discussing how large the clumps you would expect to form through this process are. And the only point here is that these current simulations, at least, suggest that you form very large bodies in this way. So typically objects perhaps the size of Ceres, which is the largest asteroid in the asteroid belt. So this is potentially a way of forming 100-kilometer-sized objects fairly directly out of things that are initially only centimeters in size. Okay, so I think I'll just finish up there with a bunch of questions. This streaming instability is thought to be an important process in protoplanetary disks, and perhaps the best way of getting over these difficulties of forming things at early times. but we're really not exactly sure how it works. So there's still a lot of work to be done to really understand how this works and whether these predictions, for example, of forming very large objects out of the streaming instability are a robust conclusion or something that actually depends on other disk parameters that perhaps we don't fully understand. Thank you.
My question is, can we consider the radial velocity gas to be zero in the case of a dead zone?
Okay, so the question is, should we consider the radial velocity to be zero in a dead zone? It will probably be close to zero. So, at least if we're considering the midplane of the disk and therefore, where the solids would be. So probably there's some residual turbulence even in a dead zone and corresponding a little bit of radial velocity. But the radial velocity in a dead zone, yes, will be maybe 2 orders of magnitude lower than it would be if we didn't have a dead zone, would be the normal expectation.
Other questions?
So, going back to the Stardust problem, you said that the radial drift upstream doesn't quite work to resolve the problem. So, I've also heard some people talk about this conveyor belt mechanism when you process concentrates at high temperatures closer to the disk, but then there are outflows carrying them away. Is that a viable mechanism, and are there other alternatives?
Yeah, so the question was about those Stardust results, and there's another mechanism that's been proposed where the transport is not within the disk, but is above the disk. And so indeed, the idea there would be that there's an outflow from fairly close to the star that takes these high temperature materials and blows them out, and some fraction of them rain back down on the outer disk and get incorporated into the cometary material there. And so I think that that is certainly a possibility for what is going on there. I mean, the basic question is how efficient that is, right? Because if the particles are very small, then the wind would actually accelerate them to terminal velocity and they'd be lost. Okay? If they're too large, they won't be accelerated in the wind. So it depends somewhat on the properties of the wind to get to a regime where the particles that you see, which maybe are up to 20 microns in size, are thrown outwards sufficiently vigorously enough, but actually rain back down on the right part of the disk. But yes, that's, I would say, the best non-disk way of trying to mix these things. And since the disk mechanisms don't seem to work very well, that's maybe a good idea for what's going on.
Do we expect, like say in these Simon simulations you just showed us, do we expect the streaming instability to be enhanced by, say, MRI turbulence, or would it tend to inhibit this quantum process?
So the question was whether the MRI turbulence would tend to inhibit or not inhibit, help the streaming instability. So I should say, first of all, that the original calculations of the streaming instability by Anders Johansson and collaborators were done in the context of MRI turbulent disks. So they found it could operate in those circumstances. The basic limitation will be that if the disk is too turbulent, then you won't get much vertical settling, and vertical settling will help in getting to the conditions where the streaming instability operates vigorously. So there's sort of a whole bunch of things that contribute there. Really, to get the streaming instability to work, you first of all need large enough particles, which is a collisional growth question. You also need a high enough density of those particles, and in principle, that density could be attained either through vertical settling or through some kind of radial concentration process. So if you have a very turbulent disk, the vertical settling will be off the table, and you'd have to rely instead on the radial process to get to the point where streaming instability would operate quickly.